Hello, a very warm welcome to all of you. So now in the previous video, we have watched how to solve about the transfer function of a field control DC motor. In this lecture, we will be studying how to solve the transfer function of the armature control transfer function for armature control DC motor. So if you will look at the armature control DC motor transfer function, we will see that the transfer function would become closed loop system. It will be a CLS, closed loop system, whereas the DC motor transfer function was open loop. Here what happens is primarily the field flux is constant over here, okay, and whereas the armature equation we will be governing. So this is constant, the flux to the field is constant over here. So we have current IF, RF in the field winding, we have LF here, and the armature side is connected here, wherein this is our motor side, this is the motor M, and again for the armature we have RA, we have the term LA, okay, and then we have the term here, you can see the term that is your EA, okay. So this is your plus minus EA, RA, LA, and you have the direction of the current as IA. So I'll also just write down the direction of these signal plus minus, and similarly this is minus and this is plus, okay. So it will go like this and plus minus. So now you have to write wherein the terms here is the torque, mechanical torque, then this is the inertia, then this is the friction coefficient and the angle theta m. So here when we are solving this term, so remember that this is produced due to this flux that will be generated here would be constant. So Kf and If will remain, field circuit is constant, okay. And now the torque produced just like the earlier case would be equal to, here also the same thing, we will write the term K dash in terms of, because torque produced would be K dash phi Im into Ia. So the same thing, this K dash, if this is your equation 1 and put equation 2, the value of phi m from equation 1 here, so you'll get this as K dash Kf If into, sorry, If into Ia. So here notice there is one big difference here in comparison to the other values over here. So you have this value here in terms of K dash, Kf, If and Ia. You can also write this term. This is a constant variable. Okay. So this term can be given any name. So in some books it is written K dash. If it is K dash M here, so let it be K dash M here. If it was K dash Km, then it would have been Km only. So now one important thing is that you in the previous lecture I told you your this EB is equal to K phi omega, okay, wherein the value of K I have showed you was equal to P Z by 60A, where this was the pole, this was the denominator. So we are not interested in that. Here we are interested. Here if you look at this equation clearly, the flux value is constant. So we can write that EB is equal to K omega, right? Directly we can write. And the previous equation also I have shown you the omega value was equal to 1 by S theta m. So we can write the value of omega m, because 1 by S, okay, would is a sign for different integration. So we can write the term theta m in terms of uh, this, sorry, this was equal to omega m was equal to S theta m, not 1 by S. So in the last class also this is S theta m. So this S theta m can be written as omega m can be written as d theta m by dt. So this is one of the equations there. Now you can have this value of omega m, okay, or this EB omega m value I can substitute here. I can write this equal to KB into S theta of m. Okay, this value I have written S theta of m. Okay, in Laplace domain, this can be written small s. It is not necessary, but you can write it. Now, can you write the differential equation here? You see here, EA is the term that is going in, rest all is the fall in the circuit. So you can write EA would be equal to EB plus IARA plus LA DIA by dt. So this equation again, this from this equation number 3, this is 1, let this be 2, let this be 3, and let this be 4. So you write the Laplace domain equation for this. Let me write it in the next page. Okay. So the Laplace domain equation for this would be given in terms of EA of S we had, and only the term wherein there would be one extra S would be the S term, would be with respect to the inductor A of S. Okay. And we have RA plus S LA IA, and the rest term is okay. That is done. We are done with the equation. So we can write this in terms of IA. We can write this equation IA of S would be equal to EA of S minus EB of S divided by RA plus SLA. So we have this term over here. But what was the torque value? The torque value that we generated in the previous slide was equal to K dash M KF IF into IA. Right, so this value of IA from equation 4 we can substitute in equation 5. Okay, so this value of IA would be K dash M KF IF, and this value is equal to EA of S minus EB of S divided by RA plus SLA. So once we have arrived at this equation, EB equation also from the previous slide, what we had calculated, EB was equal to KB S theta ms. So this value can be substituted here because we want the ratio in terms of theta m and EF. EF is the input, whereas this is the output, just like in the case of the this motor. So once I'm substituting these values there, I can rearrange these equations. Prior to writing these equations, I had the common equation which was previously also written there for the motor, that is Jm d square theta m by dt square plus Bm d theta m by dt. So this term could have been in the Laplace domain. It is written as Jm s square plus Bm, okay, SBm, right? SBm, because d by dt means s and d square by dt square means s square time, and again I'm repeating it. Okay, so this is Tm is equal to Gm s square plus SBm, and the other value that we are left with is theta m of s. So you can see this equation 6, okay, and equation 7. You can compare this equation after putting the value of EB is equal to KB s theta ms. Here you can compare the equation. So I'll directly take the new page wherein I'll be comparing these equations. So let's compare the equations. So I have these equations as, yeah, let me take the pen. So these equations as Km dash Kf If Ea of S Ra plus SLA is equal to, here if I substitute the value of, okay, different values of see Km Kf IF is okay. For EA, if I substitute the value, I'll get it as KB of S. So I'll be substituting the value KB or S theta m of S. So I can write this as Km dash KF IF KB S theta m of S would be equal to RA plus SLA. This would be equal to plus JM S square plus SBM. Common term, there would be theta m of s. So I have compared these two equations. On one side of the equation, I'm writing this torque equation, then I'm opening this equation here. Okay, once I'm opening this equation, I get the final equation in the form of, I want it in the form of theta m of s by EA of S. So I can rearrange this equation and write in this form. Write in the GS 1 plus GS HS form. So in order to write this, I can rewrite this equation. I can write it as Km is equal to SRA BM 1 plus STM. Same thing, like TM was equal to what? TM was equal to GM by BM. Here also TM is equal to the same thing, plus STA, okay, divided by KM into SKB divided by, yeah, sorry, plus 1 plus, yeah, this is the GS term. Okay, now GS term will repeat as it is SRA BM 1 plus STM 1 plus STA, and this SKB term, extra term, here is the HS value. HS value is your SKB term. Now I can express this equation in the closed loop form. How I can write this equation is that I can write the entire equation by putting the same value. Tm is equal to Gm by Vm, and for tau A is equal to La by Ra. Now this Km can be segregated into Km dash into Kf. So this Km dash into Kf, what you are seeing there on top of here, can be segregated into one single value Km, which I had just forgotten there. So Km would be equal to, and now you can write this entire equation in terms of GS value we have. So GS value we have as Km S RA BM 1 plus STM 1 plus STA, and HS value you have as SKB. So HS value you are having as SKB. So now you can reduce this equation into the closed loop form, wherein the input is EA, which is going inside a summation block, which is acting as a comparator, and from there you have the first value of the GM value of the torque comparator, which can be expressed as Km S BM 1 plus Tm of S. So Tm of S value you have mentioned over here. Then you have another term, that is your 1 by Ra 1 plus STA, which can be segregated from this equation after substituting, and then you have this term theta m of S. This is returning back to the system, and you saw the feedback H of S. I had already written SKB. So this is the feedback SKB, and now if you clearly look, the system is a closed loop system. System is moving in this direction, then it's coming back. The output is getting compared with the input, hence it's a closed loop system. So armature control of a DC motor would be a closed loop system. Okay, so this is it. I'm ending it here. Thanks a lot. If you like it, it's good. If you don't like it, it's also good. Okay.